Good afternoon. I see some of you. How many in the room know thermoreflectance? Okay, so at least one. So if you don't know, at the end of the show there is a present if you can figure out what that is. My name is Shakouri. I'm the CEO of MicroApps, and this presentation is jointly with Sidina Wane from EV Technology. We'd like to share with you some of the trends and dynamics regarding thermal analysis and how that needs to be looked at for over the air and also microwave devices. So one of the fundamental things about thermal imaging is the following. As you develop circuits design, you start with material, you developed packages, and you want PC board. One of the fundamental tools is to really understand inside each level how the material and device is coming together. So what we have developed is an optical technique. So we call it EMS scope as like a microscope. So that allows you to look at the energy of thermal. By looking at the thermal energy, you can see in optical techniques sub-micron resolution. And then in addition to that, there is an invention of a new material chemistry that can convert electromagnetic energy to temperature. By using that technique, we can use the same thermal camera to look at the devices under test. So if you're not familiar with thermal imaging, infrared, and most of you have heard, I'm sure, is very familiar. The challenge is very slow and is also not the highest resolution. What we develop is what is in the middle called thermoreflectance. Thermoreflectance means that if you shine light on any surface, the reflected light depends on the temperature. Because we can use near UV or visible light, we can get higher spatial resolution. So from that level, you can see inside the circuit the geography. Using the technique like this, we can achieve hundreds of nanometer spatial resolution, which is you can see in the gate of the transistor, and we can measure 500 picosecond transient. We can start seeing how current move on a gate of the transistor. It is one of the most important thing about this technique is calibration. In our booth 1407, we have a live demonstration, so please come and visit us to see that. Another thing that is really important in here is the idea of averaging and be able to improve the resolution so we can get 0.01 degree Kelvin. You can get really good accuracy and understanding of temperature. So I hope this gives you what I call first order perspective of how do I use optical imaging, which is physical, and thermal imaging in order to add chemistry to be able to look at material. Now I think what I like to do is, as Sidina, as a user, look at how they have used this kind of tools in applications that is microwave used.
Thank you very much, Mo, for the introduction. So we have actually deployed this technology in collaboration with MPI. So MPI is a leader on probing stations. They develop probing technologies for on-wafer measurements. And the technology that Mo has presented is already deployed in their platform. It is mainly deployed for self-heating, for analyzing transistor level dissipation, but it is also used to look at the analysis at package level. And that analysis is very important for temporal resolution in time domain. It gives you also the possibility to conduct failure analysis. Failure analysis related to temperature, and that is a very important tool for defect mapping and wafer uniformity, and it was already deployed, and I invite you to have more information about that. This is just a very simple illustration showing you at chip level and package level how the thermal dissipation can be used, and this was a demonstration with MPI where you see how this microsense imaging system was integrated within their platform, with the probing. And actually, the optimization of the whole platform work was done to avoid the collusion between the microscope itself and the probing. So they have a very low profile RF probing that makes use of those type of technology. And you see here on the left side an application where we have been using system in package technology with a power amplifier, a low noise amplifier, and you can see in real time, in time domain, how the power and the dissipation flows through the circuits. Much more higher resolution is seen on the bottom side, where you can almost see the power within the transistor itself. We have pushed actually the analysis farther in checking how this type of devices can be combined with antennas, how it can be combined and checked against the packaging technology. On the right side, what you see is the wafer level chip scale packaging with bumps, what is used with an RDL, a redistribution layer that is sitting between the bumps and the IC itself, and this is extremely critical. It is critical for the optimization of power dissipation, but up to now, the IR camera cannot do that type of analysis for two reasons. The first reason is the resolution cannot allow it, because you need to go down in resolution at chip level. And the second reason is that in general, from the backside of the chip, there is no technology that helps to see what the heat is. And with MicroSense, we have demonstrated the possibility to measure the thermal dissipation at the bottom side of the chips, so that you can see directly from the substrate with the transparency how the heat is going into the gates of the transistor. What you see here is a practical application of GaN with 365 nanometer in UV and 530 nanometer illumination. And you can recognize the width about 4.5 microns, and you can see actually the heat flowing through the device itself. And this double selectable lambda 4 gold pad area analysis. And this is actually not achievable with IR type of analysis because of the resolution. And in time domain, what is interesting is you can look at the shooting and the power on, power off, and that thermal events occur more rapidly with smaller devices features. That's why for advanced technology like the FDSOI 22 nanometers, or even in the FinFET, this technology would be extremely useful, because you can proc actually the heat dissipation at the gate level. And that is important, mainly when you will have the packaging added to the system. Because at a given moment in time, optimization of the thermal resistance will help you to see really among the interfaces where the things are happening. And that is given by time domain analysis. And that time domain is illustrated here, where you can see between the GaN SiC itself, the die attach, and the PCB with the solder mask in between, that you have lumped elements that give you a complete analysis of the thermal path, creating the compact model. And you have a compact model that gives you a link to the physical interpretation. Now, from chip package level, an IC and antenna comes up the question of power dissipation and following the path of the heat. This is a very practical example of a Wi-Fi device working at 2.4 gigahertz, where we have been looking at the power on, power off of the devices. So this was done by really looking at the switching of the battery in real time, and we could follow the path of the heat. That might be also interesting for looking at ESD, or for looking at some glitches that is coming from the interaction between the power dissipation and the RF itself. We pushed it also farther, that you see here the glitching of the laser itself. We put it farther to see how this can be actually used for antenna in package type of applications. So what you see on the right side is an iPhone, a user equipment type of application, where actually you have 4 antennas, 1x4 antenna elements, and we were able to use the thermal analysis to detect 40 antennas. So this is not aimed to have very accurate radiation pattern. It is mainly used to detect 40 antennas in a production line, so that you can be very fast and you can be extremely effective in selecting the right devices and in getting into the root cause if there is a problem. So we pushed it actually at the next level of comparing the thermal near field measurements versus classical optical probing measurement techniques. And we even compared it to 3D full wave analysis from CST HFSS of Ampere. So CST is operating in time domain, CST and HFSS in frequency domain, but Ampere is also operating in time domain. So we were able to compare in the near field, the crossing of the antenna level, how the level of the pointing vector, which is actually linking it to the square of the electric field divided by the impedance. And we compared that in the near field at 5 millimeter from the DUT. Why 5 millimeter? Because 28 gigahertz, the wavelength is 10 millimeter. If you want to be lambda over 2 from the device, then you need to be 5 millimeter from the device itself to get the right focus. And based on that distance, we were able to measure the electric and the magnetic field. What you see here is actually the wave impedance, which is the ratio of the electric field and magnetic field. And we know that that radiation impedance should be 377 ohms when you go in free space. So continuously you can see how that impedance changes. How we measure the impedance? We measure it using a near field probe in optical domain, and we made sure that we are really in the near field reactive zone to have the ratio between the two. What you see here is the correlation between the thermal response and the square of the electric field, which is actually an image of the pointing vector itself or the power density. And you see that the two responses are very similar. On the left side, we have excited antenna by antenna sequentially. Port 1 is for antenna 1 and port 2 for antenna 2. And what you see is when one single antenna is excited, the delta T, which is the difference between the power on power of differential temperature, is shown in real time, and you can see that correlation between the energy density and the thermal dissipation. Now, we do think that this can also open the door to the testing of antenna in package solutions for beamformers. So what we have done is to excite a beamformer at 28 gigahertz sequentially. How we do that sequentially with SPI type of control, you can access each element separately, and you can see in real time each element being excited, and you can see the dissipation due to losses of the antennas, and you can link it actually in real time to the power that is heating the antenna itself. So this was for the fourth antenna excited, the fifth antenna, the sixth, the seventh, and the eighth, but you can also excite the full row. And what is interesting is that that can be used to calibrate the phased array in terms of power. Why this is important is even if the phased array is functional, the peripheral antennas and the inner antennas will never deliver the same power because of adjacent coupling. So the inner antennas have 4 neighbors. You have proximity effects. The peripheral antennas will see different boundary conditions. They have only one single neighbor. So by looking at the dissipation, you could actually correlate that power level, and it can be a very easy way to calibrate the power levels at least the DC. And we have checked the combination of this type of antenna with front-end modules from IMS, and that demo is showing you how in the transmit mode we can also take into account the biasing of the system in real time, so that in the power on power off, the switching time is compliant with the triggering of the system. Why triggering is essential is because in microsense, you need to hook up the excitation to the device, so you need to control the device in order to power it on, power it off, so that it can cool down. And that process will give you the possibility in time domain to look at the power on, power off sequence. And this is the type of analysis that we have conducted, and that will open several possibilities for induction process. So we have in our booth running demos in real time. So we invite you all to come up. It's 1407, and you will see our team is available to answer to your questions, or if you have your own device, we encourage you to bring it, and we will be able to show you in real time how it works. So let me conclude with that. We have proposed actually with this technology a unified platform for both reliability testing and functional testing. It is extremely fast, and it is compliant with production line testing. And at the same time, we have high accuracy temperature calibration, and it is compliant with the coating technology that we have proposed based on this spin crossover analysis. And it will enable the heterogeneous 3D packaging technologies where actually it's very challenging to get the heat out. And it can also help device and engineers to optimize their devices in terms of power, energy, efficiency. And it can be hooked up also to the modeling devices. Why it is important to get this back to the modeling? Because the designers are always interested in the next generation of devices. So they want to use the experience from the previous device release to improve it, and that thermal analysis can be used as a source to optimize the next generation packaging, and it will be very useful to bridge it to the modeling and the design tools. Thank you for your time.